about imaginary numbers? I mean, if they're imaginary, then why should we even bother? Well, in actuality, imaginary numbers aren't imaginary at all. In fact, they appear in a lot of our fundamental understanding of physics. But first, what is an imaginary number? An imaginary number is basically representing a square root of a negative number. Now, there's no real number that we have that can represent this value. So, we use a placeholder called I. Now, I, being square root of -1, behaves a lot more differently than regular numbers. See, if we raise a regular number to an exponent and keep increasing, what we see is that the number keeps exponentially increasing. However, with I, it keeps going back and forth between a certain set of numbers. But why is that? Well, this is because the imaginary numbers exist in an axis that is perpendicular to our real axis, what we call the number line. Multiplying by I essentially rotates the point. This gave discovery to complex numbers, which are basically numbers across a point in this axis. And multiplying by a complex number would effectively rotate it by adding its angle to the real axis, multiplying its distance from 0. Now, why is this important? Well, for that we have to go to Euler, who was analyzing something called the Maclaurin series, which was a unique way to describe trigonometric functions, and he used that for e to the x. Now, what he did was he introduced I to that expression, and what he found was that it could be simplified to cosine x plus I times sine x. In waves, there's a concept of a phase, where basically we are looking at a location of a point relative to a crest or trough, and two corresponding locations are in phase with one another, and those that are not are some degree out of phase. This is important because these waves are usually described by sinusoidal functions, which are difficult to do math with. But if we play with the math a little and use Euler's expression, what we find is that these wave functions can be represented by e to the I times a certain angle. And this is useful because it's much easier to do calculus with e than to do with trigonometric functions. Now, this led to e to the I times something coming up in a lot of physics concepts, including especially Schrodinger's equation, which shows that I is not imaginary. It's as real as any other number, and it appears in our understanding of physics. So,